Okay, here we go again. Third week, lecture B, and we are well and truly into the deep end by now. So let's not waste time and get into it. So there is basically 4 points that I want to discuss with you in this lecture. As I will always do, I'll give a little bit of a recap of where we are and what we have learned so far. So I'll give you a recap on multiple regression analysis, which we introduced in the last lecture. And then I want to elaborate on a few topics that I already introduced in the A lectures. I'm going to elaborate on standardized coefficients. I'm going to elaborate on having nested models, and I'm going to elaborate on this problem of multicollinearity that we discussed in the A lecture. So let's start with the recap. So by now we have seen that we can extend our simple linear regression model into a multiple linear regression model. And it's multiple because in a multiple linear regression model, you have multiple x variables that you include in your model to explain your y variable, your dependent variable. So in general, these multiple regression models take the form of yi equals b0, the constant value, plus b1 x1i, so the first coefficient for the first independent variable, plus b2 x2i, the second coefficient for the second independent variable, and so on and so forth, until you have all the coefficients for all the independent variables that you have included in your model, where k stands for the number of independent variables or x variables that you have included in your model. And even though by including more x variables in your model, you're probably going to do a better job of explaining your dependent variables, so explain more of the differences, the variation, or technically the variance of your dependent variable, we still don't assume that we will ever be able to explain all of the differences, all of the variance. So there is still the error term included that allows for a difference between the values we would predict based on our model for each case and the values that we actually observe for each case on the dependent variable. Yeah, so that's the basic shape of the model. And we have seen that one of the reasons this is a very useful model is because by including x variables in the model, we are controlling for differences in those x variables when we look at the coefficients of the other variables that are in the model. So we can estimate the effect of more than one x variable on our dependent variable. And for each x variable, the coefficient that we get is the effect of that x variable controlled for the effects of all the other x variables in our model on our dependent variable. Which is often quite useful, especially if you have hypotheses based on causal reasoning, causal mechanisms, causal theories, because then the hypothesis that you're trying to test is a statement about a causal effect. So you want to have the best possible estimate of that causal effect, and we know that often in practice we work with data where lots of other things might have an effect on our dependent variable, and sometimes these other things might have an effect on both our dependent variable as well as on our independent variable. In that case, they are really confounding variables. So if we would not be able to correct or control or adjust for differences on those other variables, the estimates that we get for the variables that we have hypothesis about would be not good reflections of the true causal effects which we are actually interested in testing. So the idea is that, well, if we can measure those other variables, we can include them in the model, and we can, by including them in the model, we are controlling for the effects of those other variables in the model. And then we know now that our coefficients represent the effects for each x variable on our dependent variable that is unrelated to the values of the other x variables in our model. We have seen that we can still use OLS as an estimation method to get the right values for B0, B1, B2, all the different coefficients that we want to find values for. So we can still use ordinary least squares estimation, so minimizing the sum of squared residuals to find the right values for our B coefficients. We have also seen that, now we can still talk about the goodness of fit of our regression model. So for instance, we can still look at the R squared, the coefficient of determination, as a measure of how well our model fits the data. And what does it now represent? Well, it represents how much variance in our dependent variable we are explaining with all our x variables that we include in the model combined. So that's now an overall measurement of how much variation we are able to explain, how much variance we are able to explain with the variation in our x variables that we included in the model altogether. And of course, we can still look at, say something about the individual coefficients in the model. And we can still use the t-test, well, to evaluate statistical significance of all these individual coefficients. So we can still say, well, we have a coefficient for our first independent variable, x1. That's going to be estimated, so it takes some value. We're also going to get an estimate for the standard error of that coefficient. Well, we can still take that coefficient and divide it by the standard error to get a t-value for the null hypothesis that the effect of that specific independent variable in the population would be 0. And then we can see, well, how far out in the tail of the t-distribution is that t-value to get a p-value, which tells us, well, what is the probability finding this t-value or a higher t-value under the assumption that our null hypothesis is true, that there is really no effect of that x variable on a dependent variable in the population. And then if the p-value is low enough, we can maybe reject that null hypothesis in favor of the alternative hypothesis that there is some effect, or maybe even that there is a positive or a negative effect if we have a directed alternative hypothesis. One thing that I did not yet discuss is, well, what is the appropriate degrees of freedom for that t-test? Remember, the t-distribution is not just one distribution, it is really a family of distributions. So there's all kinds of different t-distribution, and the shape of all those specific t-distribution depends on the degrees of freedom that you're working with in your theoretical sampling distribution. And thankfully, we have the mathematics to show exactly what is the correct degrees of freedom for different situations. And if you're doing this in a regression model to test regression coefficients, the degrees of freedom for your t-test are given by n, your sample size, minus k, the number of x variables in your model. Yeah, so sample size, how many observations you have, minus k, how many variables did you put into your model, and the -1, and the -1 is because you're also estimating the b0, the constant value. So there is one extra parameter estimate that we are trying to get, so that defines our degrees of freedom. So that's the relevant t-distribution that we are looking at. Again, SPSS automatically checks the right one for you for these models. So in that sense, you don't need to worry about that. But you should be aware that also there it depends on your sample size, the number of independent variables, exactly what t-distribution we are looking at. If it's a very, very large sample size and the number of independent variables is not super large, then the relevant t-distribution will be, of course, very, very close to the normal distribution. Yeah, remember the t-distribution is like the normal distribution, but just a bit flatter, allowing for wider sampling distribution, so more uncertainty. But the larger your sample becomes, the less of that uncertainty you have to deal with, so the more the t-distribution looks like the normal distribution. You could say if you have an infinite amount of observations, then there's no difference anymore between the t-distribution and the normal distribution. But of course, this becomes relevant, this degrees of freedom, if you're working with smaller data sets. Also if you want to estimate effects for lots and lots and lots of different x variables at the same time. Let's elaborate a little bit on something that I already touched on in the previous lecture, and that's the idea that we can interpret our coefficients on the original scales of the variables that we're working with. And then we're talking about the unstandardized regression coefficients. But we can also translate our variables into standardized scales, so translate them into z-scores, and then we can express our coefficients as standardized coefficients. So why would you want to do that? That's something I want to address now, because, well, it's nice that we can have it in standardized shape and unstandardized shape, our coefficient, but yeah, why? If both mean the same thing and represent exactly the same information, why would you even have two different ways of expressing your coefficient? And one reason that might be useful is if you want to compare effect sizes of your x variables. So if you have different x variables that you include in your model, different independent variables, and you want to say, well, which one of these has the larger effect, which one of those has the largest effect, which has the smallest effect. So get a sense of which variables have are working better in predicting your outcome, and your dependent variable are working worse in predicting your outcome. Yeah, and there is a problem with trying to do that by looking at the unstandardized regression coefficients, because the value of our unstandardized regression coefficient, well, it's expressed in the scale of the variables that we're working with, the original scale, which also means it completely depends on the scale of the variables that we're working with. So the value of our unstandardized coefficient, our B coefficient, depends on the scale of our independent variables. And to illustrate that, I have an example. And this is something that I actually did with some old version of the European Social Survey data. I estimated the effect of age. Well, remember, age is measured in years in the ESS. So for each case, each respondent in our data set, we have a value for age indicating how old they are in years. And so what I did is I estimated the regression model, and I took x as an x variable age. So I included age as an independent variable, and the dependent variable in this case was satisfaction with democracy. So trying to explain differences in satisfaction with democracy by looking at differences in age. And the regression coefficient that I found, so that SPSS gave me, was b equals minus 0.004582. So a negative coefficient telling you that for every increase in age in 1 year, so for every additional year, for every year older a person is, the predicted value on satisfaction with democracy decreases by 0.004582 points. Yeah, satisfaction with democracy is measured on a point scale, so the predicted value is then expressed as points. Yeah. So a slight negative effect. And then I did something interesting, you could say. I made a new variable. I included a new variable in my data set, and that variable was just the original age variable divided by 10. So for each case in our data set, each survey respondent in the European Social Survey for the Netherlands, I took the age of that person, of that case, and whatever that number was, I divided it by 10. So if a person was 30 years old, then I divided that by 10, and so then I have a new variable in my data set for that person. The value would have been 3. If a person was 55 years old, I divided that by 10, and so the new value on that new variable, age divided by 10, would have been 5.5. And then I re-estimated exactly the same regression model. So I just used, instead of age, I used age divided by 10 as an independent variable. Now stop and think. What do you think is the value of the regression coefficient that I found? Okay, if you figured this out, you are really, really smart. That's great. Don't worry if you didn't. But this is what I found. I found a regression coefficient of minus 0.045820. And now notice that the difference between the coefficient for age and the coefficient for age divided by 10 is basically where the 0 is. Yeah. Basically what we have here is a regression coefficient that's the original coefficient multiplied by 10. Which if you think about, makes sense, right? We changed the age scale from years to years divided by 10. So basically, we made that scale a lot smaller. Yeah, made it 10 times as small. So and the regression coefficient still captures exactly the same age effect. Yeah, because the relationship between age and satisfaction of democracy didn't change. The only thing that changed is the scale on which we measure age. So of course, the regression coefficient had to grow by 10 times in order to deal with that new scale and still represent the same relationship. I, for instance, also did that with a new variable where I divided age by 100. Yeah, so I created again a new variable, and then for each observation that I had, I took the value of age, so how old the person is, and I divided that number by 100. So a 100-year-old person in our data set would have gotten the value 1 on that new variable, and then I re-estimated the model, and this is the coefficient that I found, b equals minus 0.45820. And again, it is really the same coefficient. The only thing that changed is where the 0 falls. So now we have basically further reduced the size of the scale of h. So we divided it by 100, which means that to represent the same underlying relationship, our coefficient again had to grow now by basically by 100 by times 100 to still represent the same underlying relationship. Or what I could also do, what I also did, is I divided h by 1000 and to use that as a new x variable in my model, and then re-estimated the same effect. And now I got a coefficient of minus 4.5820. Yeah, so again, I changed the scale of h. The relationship between h and satisfaction of democracy didn't actually change. I still have the same observations. There's still the same differences in h and the satisfaction of democracy and how they go together. So basically the covariance of h and satisfaction of democracy didn't actually change, but the scale of h did change. So the coefficient again has to grow along to accommodate now this different scale, this h divided by 1000 scale. And yeah, I also tried with what would happen if I multiply h by some number. So I tried with a new variable where I multiplied the values of h by 10. Yeah, so if a person would have been 20 years old in our data set, that person would have gotten the value 200 on this h times 10 variable. And then again, I re-estimated the model. And again, stop and think, what do you think was the value of the coefficient that I found? Yes, now it was minus 0.000458. In other words, what I did is I blew up now the h scale, made it basically 10 times as large, and it still has to reflect the same underlying relationship. So the coefficient now had to become smaller by 10 times. So I get an extra 0 compared to the original h effect. And what that shows you is basically that we can't just look at the value of our coefficients, of our unstandardized regression coefficients, to say something about the effect size of our independent variable compared to other independent variables in our model, because different independent variables will be measured on different scales. And so that alone will already create different values for our coefficient. So we might find a small coefficient for one x variable and a large coefficient for another x variable, but that might have nothing to do with the fact that one of those is a much better explanation of our dependent variable than the other. It just might have to do with the fact that they are measured on very, very different scales. Maybe one is measured on a very, very wide scale and another one on a very, very narrow scale, right? So that's a problem. And there is, of course, as always, there are solutions to all the problems that we have. Some work better and some work worse. And this is one that I have to teach you about because it's in the book. It's in most textbooks, and it's something that is used also in practice quite often. And that's the solution of, well, if we can't compare our unstandardized coefficients because the scales of our x variables are different, then why don't we get coefficients that are based on a comparable scale by using standardized coefficients? Yeah, remember, what are standardized coefficients? They are basically the coefficients you would get if you would transform the raw scores on your independent, your x variables, and your dependent, your y variables, into z scores, into standard scores, because then they are comparable, because now we have translated all these raw observations into deviation scores from the mean scaled to the standard deviation of our variables. Yeah, so x minus x, x for each case minus x bar, so the observation for each case minus the average on that variable divided by the standard deviation of that variable. So z scores, right? So we can also do this if we have more than one independent variable in our model. So basically translate our multiple regression model from a model for unstandardized coefficients into a model for standardized coefficients. Again, like I said in the previous lecture, if you standardize all your variables, then the constant in the regression model, so the B0 coefficient, will be by definition 0. That's just a mathematical consequence of standardization. So you can just drop that from the equation then. So there is no need to estimate B0 because by definition it can only take one value, the value 0. So we can just forget about this B0 coefficient. But all the other coefficients will be in our new regression model for standardized coefficients. And now we can at least somehow compare the values of B1, B2, our so-called, sometimes called beta coefficients, our standardized regression coefficients, because now we have translated the original scales of our x variables that are not comparable into scales that are comparable between different variables, because we transformed them into z-scores. And you could say then, well, roughly, if my standardized coefficient for one variable is larger than for another variable, so if my standardized coefficient for x1 is larger than for x2, that basically means that x1 is better in explaining variation in our dependent variable than x2 is. Yeah, so it is a better explanation of our dependent variable. So that's the reason why we have these standardized coefficients. That's also the reason why SPSS will automatically calculate them for them, because they might be useful if you want to compare effect sizes between different variables that you have in your model, right? So of course, there's also a formal interpretation to our regression coefficients now in a standardized model. And here, as you have already seen the last time, well, if you have a standardized coefficient in a simple linear regression model, then it's identical to the correlation coefficient. And how do we interpret that? Well, it's on a scale of standard scores, z-scores. So that's basically standard deviations relative to the mean. So again, we can extend the same interpretation now to these unstandardized coefficients in multiple linear regression models. So each coefficient tells us with how many standard deviations the predicted value on our dependent variable increases. Yeah, our dependent variable now is measured in standard deviations. So with how many standard deviations the predicted value in our dependent variable increases, with a 1 standard deviation increase in our independent variable, in our x variable, because also that x variable is now on a z-score scale. So that means, what is the unit of the scale? What does a 1 value represent? So a step of 1 on the scale of the independent variable, it's a step of 1 standard deviation, right? So that's how to interpret those coefficients. So again, I'm going to show you an example. So this is the same model that I showed you in the last lecture. So I took satisfaction with the national government. That was my dependent variable, as you can see at the bottom of this table. And then I had HINCT-NTA and AGEA, so income and age. Household income and age of the respondent as independent variables, and we already know how to interpret the unstandardized regression coefficients and the standard errors and the t-values and the p-values. But now let's look at where can we find the rest. So we already know that these unstandardized coefficients give us the effects of our x variables on a predicted value of our dependent variable on the original scale of my independent variable and my dependent variable. So we already know where to find those coefficients, but SPSS also automatically again gives us the column beta standardized coefficients, and this is where we can find our standardized regression coefficients for the different independent variables. So for instance, the coefficient B1 for x1, which is in this case the income variable, the standardized coefficient of that is can be found in the line for household income under the column beta, or standardized coefficients. And we can also find the B2 coefficient, which in this case the second x variable in our model is age. So we get a standardized coefficient for our age variable in the line for age in the column for standardized coefficient beta, right? So we have a standardized coefficient for income, which is 0.234, which is now a different value than the original coefficient of income. And we have a standardized coefficient for age, which is now minus 0.015, which is also a different value than the original coefficient of minus 0.002. And they are, of course, different because they are expressed on a different scale. Notice that they are based on the same model. SPSS didn't even need to re-estimate the model, that you can just mathematically transform from this to this value, from the unstandardized coefficient to the standardized coefficient, or the other way around. So there is nothing intrinsically different about the relationships that are being captured. It's still the same relationship between income and satisfaction with the national government, and age and satisfaction with the national government. The only thing that changed is the scale, which is now for the standardized coefficient a standard scale. So we do get different values, of course, for our coefficients, as we would expect, because we changed the scale. Notice that there is no beta reported for the constant, again, because this has to be the value 0 by definition. That's mathematically cannot be any different value than 0. That is exactly because we did this Z transformation. So SPSS doesn't even report that, it doesn't even try to estimate that, because it would be impossible anyway, because it just is going to be the value 0 by definition. So there is no beta coefficient for the constant or the intercept in our regression equation. Yeah, so now we have these new standardized coefficients. Well, how do we interpret these standardized coefficients? Well, for instance, if we look at the standardized coefficient for the income variable, well, we know that income for that coefficient is measured on a z-score scale, so in standard deviations relative to the mean. And we know that our dependent variable is measured on a z-score scale, and we know that it's a multiple regression model, so we have to interpret the coefficient as that's the effect, holding the effect of the other variables in the model on our dependent variable constant. So how do we formally interpret this income standardized coefficients for the income variable? Well, with every 1 standard deviation increase in household income, the predicted value of satisfaction with government increases by 0.234 standard deviations, of course holding the effect of age on satisfaction with government constant, so controlling for differences in age that we included in our model. And the same thing with the income, the age effect. We could say, well, for every 1 standard deviation increase in age, the predicted value of satisfaction with government decreases. It's a negative coefficient, so it decreases by 0.015 standard deviations, holding the effect of income on satisfaction with government constant. Yeah, so in this case, we couldn't have just looked at the unstandardized coefficients and said, yes, well, income is a better predictor of satisfaction with national government than age, because the unstandardized coefficients for income is larger than that for age. Yeah, 0.166, the absolute value is larger than minus 0.0002. But that would be wrong, because, yeah, of course, it's quite likely that the coefficient for our age variable will take a smaller absolute value than it would do for our income variable, because remember, income is measured in household deciles, which basically means that the scale it's measured at runs from 1 to 10. So that's a quite small scale if you compare that to age, which is measured in years, which in our data set run from something like I think in this data set, the youngest person was 15 and the oldest 102. So that's a much larger scale, yeah, on which different values of age can vary. So it doesn't necessarily mean that the effect of age is smaller. It's just, yeah, well, the scale of age is much wider. Yeah, looking at the standardized coefficients gets rid of that problem. So we made the scales comparable. So now we can say, well, okay, yeah, we do actually in this case see that income has a larger standardized coefficient than age. So income does a better job of explaining differences in satisfaction with the national government than age does. So it's a better predictor. It has a stronger effect in that sense. Yeah, so that's why this can be useful. Of course, it could also have been the other way around. You only know when you look at the numbers, but it could have been that even though the unstandardized coefficient for age is smaller than the unstandardized coefficient for income, that the standardized coefficient for age would actually have been larger, the absolute value of that, than the standardized coefficient for income. Yeah, so that could also have been the case. Yeah, of course, positive coefficients are going to remain positive. So whether they are on the original scale or on the standardized scale, a positive effect is going to be is going to be captured by a positive number, and the negative effect is going to be captured by a negative number. So a negative unstandardized coefficient also means that our standardized coefficients will be negative, because we did change the scale, but the underlying relationship that did not change. Yeah, so of course then there still has to be a negative number. Okay, so that's the textbook solution to comparing the effects of different independent variables in our multiple linear regression models. Get them on the same scale by standardizing them. Now, as you might already guessed by the way I introduced this topic, is that I'm not that much of a fan of relying too heavily on standardized coefficients, because there are a couple of issues you should be aware of if you are using them. You need to know how it works, of course, because you will read research where it's being done, and it's not necessarily always stupid to do that. It can really sometimes make a lot of sense. You might be asked to do it yourself for your thesis research or later in your job for your research projects if you become some kind of researcher. But there are a couple of things you should be aware of when you're using standardized coefficients. One of them, of course, in order to get the variables comparable, we standardize them. And we standardize them by looking at what is the deviation score, so how far removed is each observation on every variable from the mean of that variable, divided by the standard deviation that we observed in our sample, to express these deviations on the scale of a standard deviation, so get z-scores. But of course, the standard deviation itself is the standard deviation we observe in the sample, because we don't know the true population standard deviation. So it's only an estimate of the standard deviation in the population. Which, of course, well, an estimate can be better or worse, but it is only an estimate. So it might not be a good reflection of the true population standard error. Which also means that we are basically now introducing an extra element of uncertainty in what the values of our coefficients represent. Because now the values of those coefficients don't just depend on, well, the fact that we have happened to observe this sample, but we could have taken a different sample from the population in estimating the coefficient. But now it also depends on, but also for the standard deviation, we are relying on estimates. So we just happen to have this estimate of the standard deviation. A different sample might have given us a different estimate for the standard deviation. Which of course means that it might be the case that, we now find, for instance, a larger standardized coefficient for a certain variable than for another variable, because the effect size is larger. But it also might just be the case that, well, for this specific coefficient, the standard deviation just happened to be underestimated compared to the true population standard deviation, so a smaller value than the true population standard deviation. Whereas for the other variable, maybe it was a little bit overestimated, so it's a larger value in our sample, the standard deviation, than in the population. So these differences in standardized coefficients might reflect actual differences in effect size, but they also might reflect these differences in the quality of the estimate of the standard deviation, which of course then can sometimes lead to wrong conclusions about differences in effect size. It also means that this idea of standardization has to make sense and be itself comparable. So if you have, for instance, you want to compare effects across different groups, something we'll talk about a little bit more later in the course, then it might be that there are different groups have different standard deviations because there's a different amount of variation going on among those groups, and so that itself might already lead to a different standardized coefficients you would get if you would compare regression coefficients across those different groups. Again, it's a topic that we're going to more systematically address later in the course, but that's also an issue that you can run into if you just rely on the standardized coefficients. So we have to basically have this works well if the distributions that we are looking at for our x variables and our y variable, but especially our different x variables, are actually similar to each other. So for instance, if you have, let's say, one variable, an x variable, that is super normally distributed, so we have this nice bell-shaped distribution of values on that x variable, and you have another x variable and you want to compare those variables, and that is really, really super skewed. So it's a really skewed distribution. So you have a very, very long tail on the right, on the left hand or left side of that distribution. So it's not symmetrical at all. Then really the distributions are just very, very different, and then forcing them into this mold of a z-score. The z-score itself then is also affected by how skewed your variable is. Taking z-scores of skewed variables in any case is not a good idea. Z-scores work well if the variables themselves already have a somewhat symmetric ideally even somewhat normal distribution. So if you have very, very different distributions of your variables, that can also make it difficult to say, well, is the standard coefficient, to what extent is that, do we get that value because of the underlying true effect size, and to what extent does it just have to do with differences in the distribution of our variables. That's one drawback that you should be at least somewhat aware of. Another drawback is that, well, of course, now the interpretation of our coefficient actually became a little bit more complicated, because now we have to interpret the coefficients as reflecting effects on the scale of z-scores, on standard scores. So again, it doesn't really matter for the underlying effect, that stays the same, but it is a little bit less intuitive if you have to interpret a coefficient in terms of my predicted value on my dependent variable is going to increase by so many standard deviations if my independent variable increases by so many standard deviations, because that implies that you already really are familiar with the idea of what is a standard deviation, what is a z-score. Whereas the unstandardized coefficients are just on the original scales, so that makes the interpretation a little bit easier and a little bit more intuitive, usually, unless you're writing for an audience that's already really, really familiar with statistical methods. So that's also one to consider, of course. We also have to think about how do we communicate our empirical results to an audience, and think about, well, what is our audience? Yeah, so that's one drawback. A last thing, and that's more of a conceptual issue. I'm not a huge fan of the type of research which sometimes happens where people then say, well, okay, we have two theories that explain differences in our dependent variable, theory A and theory B. Yeah, some two theories, and then from both of these theories, we're going to use a hypothesis about the effect of some independent variable on a dependent variable, and then we're going to throw both of these independent variables into a multiple regression model, and then we're going to look at the standardized coefficient, and then the variable with the larger standardized coefficient has the larger effect. So that theory is better in explaining our outcome. And that is only true under very, very, very strict assumptions, and so assumptions that are in practice very, very hard to fulfill. For one thing, all the statistical issues that we just discussed need to not have happened. So we need to already have a standard deviation that's basically an equally good, ideally a perfect approximation of the two population standard deviation, and the distributions of the variables should be really, really similar, ideally even exactly the same, which of course is super unlikely to happen in practice. But it's also kind of the wrong focus, I think, for using statistical methods in theory testing. Because now our conclusion about which theory is better depends entirely on, well, what hypotheses we have happened to deduce from our theories, which will often be a pragmatic choice. Because from every theory, you will often be able to, in theory, derive many hypotheses, deduce many hypotheses. But of course, in practice, you won't be able to test all of those hypotheses, because many hypotheses will be about variables that you are not able to observe, that you didn't measure. So then it becomes really a pragmatic choice, which hypothesis are you actually formulating, which then completely is dependent on, well, what variables happen to be in your data set, which variables did you happen to measure. And so that's one. And of course, then it might just be that one variable just happens to be much closer fit to the theory for one theory than the other variable is for the other theory. So finding a different standardized coefficient might just be an artifact of the fact that you just happen to have used this variable for testing that specific theory. So that's an issue. And also, the thing is, and this is also something we'll talk about more in depth later in the course, our variables are also going to be imperfect measurements of the theoretical concepts to which they are supposed to refer. Yeah, so one of the examples that we use quite a bit is we are looking at the effect of income on satisfaction of government, and of course, there might be some reason why we're looking at that, and hypothesis about the income effect that's based on some kind of theory. For instance, like we discussed, some version of institutional performance theory that tells you, well, if people are better off, and they think, well, this is because the institutions are working quite nicely for me, then they are more satisfied with those political institutions. But then, of course, income is only one specific way of trying to measure being better off, which has all kinds of issues associated with it potentially. So it might be a very good reflection of the underlying theoretical construct of being better off, but it might also be not such a great representation. So there might be some degree of what we formally call measurement error. So that's the difference between the theoretical conceptual variables that we want to analyze and the operationalized empirical variables that we can actually measure. Yeah, so then differences in the standardized coefficients can also just reflect differences in the quality of the measurement of our variables. So I'm always a bit quite hesitant of doing that kind of, we're going to compare unstandardized coefficients to draw conclusions about which theory is better. It's, I think, much better to just, for each theory, try to systematically and as stringently as possible test that theory, and that's going to be often a much more fruitful way of trying to falsify those theories as best as we can. So test all the hypotheses that we can derive from those theories that are good hypotheses in the sense that they are really logical conclusions about what you should be seeing in your data if the theory is correct, and try to test those hypotheses as well as possible, and based on those results draw a conclusion about to what extent your theories are actually supported by the data that you observe. But it's a really conceptual issue, and there's also a bit of disagreement about that, as with many methodological questions. So that's just my take basically on that. But you should at least be aware of these issues. Yeah. So that was about standardized coefficients. Now the second topic I want to elaborate a little bit on is this idea of nested models that are introduced in the last lecture. So this is not about the observations that we have, but it is about the models that we are estimating for these observations. And now we saw with multiple linear regression models, well, we can estimate lots of different models. So we can include different axes in our models and have different types of models. And sometimes these models will be nested. And we already saw that if we have nested models, then actually we can statistically test the goodness of fit of those two models against each other with an f-test. So we already saw, and this should not read last Monday because it was not a synchronous lecture, it should read lecture A. Sorry about that. But we already saw that we can use this f-test to compare the fit of any set of two nested models. So we get this somewhat more elaborate version of a formula for the f value. And if we calculate it like that, so n minus k nu minus 1 multiplied by r squared change divided by k change multiplied by 1 minus r squared nu, so the sample size minus the number of independent variables, x variables in our complicated model minus 1, and the minus 1 is for the intercept, the b0 value that we are calculating, multiplied by the increase in r square value, so in the proportion of explained variance in the more complicated model compared to the more simple model. I remember, if you put in more variables, make the model more complicated, by definition r square is always going to increase. So we're going to look at by how much did it increase, and divide that by the change of k, so the change in the number of x variables we have in our model. So how many additional x variables did we put into our model? How many additional coefficients are we trying to estimate? Multiplied by 1 minus the r square value in the new model. So in other words, the unexplained variance, 1 minus r square. If r square is an explained variance, then 1 minus r square is the unexplained variance. So the 1 minus r square new, the unexplained variance in our new, more complicated model. And if we calculate an f value like that, then we know that this test would allow us to test the null hypothesis that r square change is 0 in the population against the alternative hypothesis that r square change is larger than 0, so a positive number in the population. So basically testing whether the improvement in r square, so how much better we are able to explain variance in our dependent variable, whether that's so large in our sample that we are saying, well, that we are able to say, well, that's really, really unlikely if we assume that this is true, that our null hypothesis is true, that in the population we wouldn't be able to explain any additional variance in our dependent variable by making the model more complicated in the way that we just did for our sample. So the corresponding p-value then tells you what is the probability of finding this f-value or a larger f-value. If this null hypothesis is true, that it's really in the population, there would be no change at all in the R-square value by including these additional variables. And then if that p-value is small enough, we can reject that null hypothesis in favor of the alternative hypothesis that that it's quite unlikely to find the increase in R-square, so in proportion of explained variance in our sample, if it wouldn't also be the case that in the population there would be an increase in the R-square if we would make the model more complicated in the way that we did by adding those variables. And you can do that whenever you have a set of nested models. So you have two models where one is nested in the other. And I already explained, well, what are nested models? How are they defined? When can you do that? For what types of models can you use this f-test? Well, if they are nested, and being nested means that you have a more complicated model and a more simple model, and you can get from the complicated model to the simple model by taking stuff out of your model, by removing strings from your model. So in this case, I used, again, a hypothetical example. So my first model, I tried to explain differences in satisfaction of government by differences in income alone. So I have a simple linear regression model in this case with B0 plus B1 income plus an error term. And then I thought about, well, maybe I can also explain difference in satisfaction of government by differences in age. And I also found a variable that measures happiness. So how happy are you on some scale? I think from 1 to 5, really unhappy to really, really happy, something like that. So I figured, well, let's just also throw in that variable. No strong theoretical reasoning there. I was really just messing around a bit, which is always a good idea, just mess around. Not for the actual research that you report, but just to get a feel of how things work. So I have two models here. And if you look at those two models, you will see that they are nested models, because model 1, where we have just income as an independent variable, is nested in model 2, because we can get from model 2 to model 1 by just taking stuff out of model 2, specifically by taking out this part of the formula, B2 times H, and by taking out this part of the formula, B3 times happiness. And taking something out of the formula is the same thing as saying we are going to give it the value 0. Yeah, if you give something the value 0, then we can forget about it, and it doesn't add anything. We're adding stuff up in our linear regression model, and adding 0 to something is just the same value. So if this would work out to be 0, then we can drop it from the equation. It doesn't have any kind of impact then anymore on our value of our dependent variable. And if you multiply this by 0, it also drops out of the equation, because then it's just 0, and it doesn't add anything to the value on our dependent variable. And so of course, the actual observations on age and happiness are not 0. They are just the observations that the individual cases score. So if we want to get from this model to that model, it's the same as saying, well, then our regression coefficients have to be the value 0. Yeah, if B2 takes the value 0, then whatever value on age the individual respondent has is going to be multiplied by 0. Well, if you multiply something by 0, the result is always 0. So then the result of this B2 times H will always work out to be 0. The same for happiness. If B3 takes the value 0, then whatever value we see for each respondent on happiness is going to be multiplied by the coefficient, which is then the value B0. Again, if you multiply something by 0, the result is 0, so it drops out of the equation. So you see here that this simpler model is nested in this more complicated model, because we can just take stuff out of the model by setting the coefficients to 0, by just assuming that the coefficients B2 and B3 have to be 0, because then we can forget about them in our formula. So these are a hypothetical example of nested models, where model 2 is nested in the more elaborate model. Model 1 is nested in the more elaborate model 2, where we are now also allowing B2 and B3, the coefficients for age and happiness, to take different values than 0. So then we're going to have to estimate those values. Yeah, so you can do this as well in SPSS. And then the next assignment, so the assignment for this week, I think, or next week, I'm not sure anymore, one of them, you will also be asked to do that in SPSS, and SPSS actually can do that for you. So you can require SPSS to not just estimate one model at the time, but estimate multiple models at the same time. And by doing that, you can also use SPSS to allow you to compare the goodness of fit of these different models with each other with the F-test. So the assignment will tell you how to do that. I'm now showing you what will come out if you do that, what kinds of tables SPSS is going to present to you. So as always, SPSS is going to start with this table that tells you variables entered and removed. And now I used this SPSS command to estimate the two models that I just showed you. So now this also becomes a little bit more interesting because now you see that indeed I have actually estimated two models. So now SPSS tells me we have 2 models that you asked me to estimate, and I've estimated both of those models. So try to find the right values for the coefficients for both of the models that you are interested in. And then it tells you in the variables entered for the first model, it tells you, well, what variables did you include there? Remember, I wanted to have in the first model just income as an independent variable. So here it says, well, HINCT and TA, the variables that we use to measure income, that's entered in the first model. But then it also tells you for the second model which additional variables have been entered into the model. So it assumes that income is already in there in the first model, so it doesn't have to tell you about it anymore, but it does tell you about, well, what are the additional variables that have been included in your second model, which in this case is age and happy. Our variable measuring happiness, again, because I wanted in my complicated model to have the effect of income, age, and happiness all estimated at the same time. Yeah, so it doesn't give you all the variables, it just tells you which extra variables you have included. But again, quite useful if you would do lots of those different models, that you have this table that tells you all exactly what do all these models that you estimated, what independent variables are included in them. And as always, you have the dependent variable at the bottom of that table, so you know exactly what model number refers to what model. So that's quite useful. So we have model 1 up there and model 2 down there. So the abstract models that we wanted to estimate, well, SPSS tells us which one is which. The variables entered tells us the independent variables in our first model, so the x's in our first model, and the second line then tells us what are the new x's, the additional variables that we included in our second model. Okay, so the model summary table is going to also show now a model summary for both of those models. So now we have 2 models, so we get a model summary for 2 different models. And I've also requested a couple of extra statistics for those models, because they are going to come in handy. So some of these statistics you already know, some of them are new. So we have, again, the first row is for the first model. So everything that is on this row for model 1 refers to our model 1. And of course, everything that will be on the second row will be about model 2. So we still have R square and the adjusted R square, which, this is for the model where we just have income included. Yeah, SPSS again tells you at the bottom of the table that the A, so this A that we have here, that this is based on the predictors that are in the model. So in this case, we have a B0 value for the constant and a B1 value for household income and nothing else. So this is the explained variance for the model using only income as an X variable, as a predictor variable. And we get the R square and we get the adjusted R square. And remember, the adjusted R square is just the R square value adjusted for the number of independent variables that we put into the model. Because whenever we put in more, it's always going to increase. Even though, in reality in the population, it might, those including those extra variables might not add anything to the explained variance. So to adjust for the fact that more independent variables always means an increase in R square, we also have this adjusted R square value that basically adjusts for the number of X variables included in the model. But of course, in the first model, we only had income, so we only had one independent variable, so there is no adjustment to be made for more variables. So in that case, if you have just one independent variable in your models, one X variable, then the R square and the adjusted R square are exactly the same number. There is nothing to adjust for. Yeah, so 0.5055, so 5.5% explained variance in satisfaction of government due to differences in income. That's the R square and also the adjusted R square value. But of course, now we also have a second model, and there we have the explained variance for our second model. Again, it says here at the bottom, look, little b. What is the little b? Well, it tells you here, SPSS, what are the predictors in the model. So we have a constant, we still have income, we also have age, and we have happiness. So that's our more elaborate second model. And again, we get an R-square value. So what is the proportion of explained variance in our sample? In this case, you see that, yes, in fact, it did actually increase because we included more X variables in our model, and it increased to 0.071. So now we are able to explain a little bit more variance in satisfaction with government because we are using more information about the respondents. We are not just using information about income, we are also using information about age and happiness of those respondents, of those cases in our data set. So now we have 7.1% of explained variance with our more elaborate model. And now you also see that the adjusted R-square value is actually not the same as the original R-square value. So the original R-square value of 0.071, that's the proportion of explained variance in our sample. The adjusted R-square is going to adjust for the fact, yeah, of course, R-square is going to increase if you put in more independent variable. So let's make that a little bit of a more realistic, a little bit of a less unbiased reflection of the R-square value that we would get in the population. And so there's this kind of mathematical formula behind that transforms this original R-square value into a lower value, and it becomes lower the more independent variables you put into your model. Again, there are different ways of doing that, and it's not exactly clear which one actually works the best, so you should take this more as a rough indication of, well, if you have to make the best guess of what would be the explained variance of this model, if I would be able to do it for the population based on what I observe in this specific sample, then the adjusted R-square is going to be a somewhat better reflection of that than the original R-square. And you now see that this is now a different number. It's 0.069. Yeah, so the adjusted R-square suggests that this model would be able to explain 6.9% of the variance in satisfaction with government in the population. But again, this is just based on that one sample that we did in fact observe, so it might be an underestimate of the true R-square value, but it should be at least a little bit closer than the proportion of explained variance we have just for the sample unadjusted. Yeah, so now we have two different values for R-square and the adjusted R-square value. SPS is also super kind in that it tells us for each of our models the R-square change that we saw in our formula for the F statistic. So the R-square change, and we get that of course in the column R-square change, which is in the general, under the general header change statistics. So these change statistics refer to changes in our models compared to the more simple model. Well, there was no more simple model than the first model we started out with, right? Because the first model was the model with using just income as an independent variable. So if it didn't indicate any kind of simpler model than that, then SPSS will just go back to the most simple model it knows and compare your first model to the most simple model it knows, and that's just taking the mean as a prediction of our dependent variable. Yeah, so if you don't provide any kind of simpler model that you require SPSS to estimate, then it will just assume that the first model, so the least complex model that you're trying to estimate, that you want to compare that model with what we could call model 0, where we're just using the mean as a predictor of satisfaction with government. Remember, we can write the mean as a model, so in this case, satisfaction with government for each case I is equal to B0, which would then just be the mean score, the mean value on satisfaction with government, plus our error term, which would then just be the deviation score of each individual case, each respondent in our data set, from that mean value. So how far removed each case is from the mean value. Yeah, so you see that in that case, the R-square change is identical to the R-square, and if you think about that, that's logical, because what is R-square? It's the proportion of explained variance. So it's the idea that we started out with a variance in our dependent variable, so the overall amount of variability we have, the differences between the cases, and now we're trying to explain those differences by including income and differences in income as an X variable in our model. And the model explains 5.5% of the variance in satisfaction with government, which also means, well, what is the R-square change? Well, we started out with explaining no variance in satisfaction with government. We only have the mean. but we have no way of explaining differences in the mean because we haven't included any additional information about other variables. So all we have here is basically a model for the mean and the deviation scores. And you, of course, hopefully remember then that these deviation scores, if we would square them and then add them all up for the observations and divide by n-1, that would be the variance. So basically this model is just a model for the mean and the variance around that mean that we did not explain at all yet. It's just the variance that we start out with. So the R-square change is then the same thing as the R-square value because, well, we're comparing a model with an independent variable to a model with no independent variables at all, where we're not explaining any kind of variance. So R-square is 0.055 and the R-square change is exactly the same value, also 0.055. It's a little bit different for the second model because the second model SPSS now compares to the first model. So model 2 is compared to model 1. So now you see that the R-square change is a different value than the R-square value for model 2. So for model 2, the R-square value was 0.071. The R-square change value is 0.0115. Yeah, and where does that 0.015 come from? What does it mean? It tells you how much more variance are we explaining in our second model, in model 2, compared to in our first model. So how much additional variation are we able to explain in satisfaction with government among our respondents by taking into account not just differences in income, but by additionally taking into account also differences in age and happiness of those people. So in other words, the R-square change is how much more variance are we explaining in our second model compared to our first model. In other words, it is this value, the R-square of our second model minus this value, the R-square of our first model, because the difference between this second model R-square and this first model R-square value is the change in R-square. So by how much did the R-square value increase from this to this? And of course, the number here you see is rounded, but if you would look at the unrounded numbers and check this for yourself with some regression output that you're running in this way, if you look at the rounded numbers and you calculate the difference between this and this, so the R-square for your second model and for your first model, then the result of that that calculation will be exactly the R-square change value. Yeah, so again, there's no magic behind these numbers. It's just convenient for SPSS to report them to us. And then we get a new type of p-value also. So you get a sig for the F change statistic. So this is the p-value. Remember, SPSS stupidly labels the p-value as sig for significance. And now it tells you, well, this is now a p-value for the F change test statistic. So the F statistic that we just saw how to calculate if we want to compare any set of nested models with each other. But of course, the first model, there is no model that we are asking SPSS explicitly to compare with. It's the simplest model that we requested. So again, then SPSS just assumes that it has to compare the first model with the most simple model that SPSS can think of. And that's just, again, taking the mean value as a predictor for our dependent variable. So this is the p-value for comparing the goodness of fit of our first model to the, let's say, model 0 or null model, as it's sometimes referred to, where we're not using any independent variable to explain differences in satisfaction with government. We only have the mean as a prediction. So we're not explaining any difference, explaining any variance. We're just using the mean as a predicted value and recognize that there is a variance around that mean. So that's all the variance in our dependent variable, which is basically the sum of our error term, our deviation scores squared and divided by the degrees of freedom. So n-1 in that case. Yeah, so if this, like I said, the null hypothesis that this F change would test is that the R-square change is 0 in the population. But for the first model, well, the R-square change is exactly the same thing as the R-square. Yeah, because again, we're comparing just a model with no explained variance whatsoever because we're not including any variance whatsoever. So in this case, the p-value that we have here, and we'll see this later, is exactly the same p-value that we would get for getting the F statistic for testing a null hypothesis about R-square. So for the first model, testing a null hypothesis about R-square and testing the null hypothesis about R-square change is exactly the same null hypothesis because it's exactly the same value. of course, this is now different for the second model. So for the second model, this F change value now tests the improvement of model fit in our more complicated second model compared to our simpler first model. So now this is testing a null hypothesis about the R-square change value that we get here. And this is now a different value than just the R-square. Yeah, the R-square is the total explained variance of our second model. The R-square change is how much additional variance are we explaining with our more complicated model compared to our simple model. So this takes a different value. So now also it makes sense that we have a different type of p-value that also tests this specific null hypothesis. So in this case, you see a pretty small p-value, 0.000, and this is rounded to 3 digits, so it's probably 0.0000, and then some number, so it's a really small p-value. So in that case, we would say, well, it is quite unlikely to find an increase in the R-square change, in the R-square value from 0.055 to 0.0171, so an increase by 0.015. If it is in fact true that if we would have had all the observations in the population, that this model where we're also including differences in age and happiness to explain differences in satisfaction with government on top of differences in income actually explains no additional differences, no additional variation or variance in satisfaction with government, again, in the population. So that's really, really unlikely. So we can, in this case, quite confidently reject the null hypothesis that R-square change, that this value would in fact be exactly 0 in the population, for the alternative hypothesis that it is a positive value. So some value that is larger than 0. That's the alternative hypothesis that you are formulating. Yeah, so again, that's the classical statistical hypothesis test that we are testing now. But this is now really a different test than a test about the R-square. So the R-square is about the entire explained variance of whatever model we are looking at. A test about the R-square change is about how much additional variance that a more complicated model explains compared to a more simple model. So it's a really different test. And that's important to recognize because, of course, SPSS is also giving us our trusty ANOVA table. And now actually there are all these numbers that we already know, the sum of squares and mean sum of squares, are now also presented for both of the models that we find, that we estimated. Again, the bottom of the table is going to tell you exactly what is in those different models. But now it becomes quite important to take this into account, exactly what null hypothesis is being tested with the F-test that we are looking at. Because now we have different types of F-tests that compare different models with each other, and this is really something that you have to learn because this is useful. You will later see in the course how we can use that to test super interesting theoretical hypotheses, and of course because it's useful and important, it's also things that you will need to know on the exam. So exactly what null hypothesis am I trying to test, and what is the relevant F statistic to test that, because now we get F statistics in the ANOVA table, but we already got also F statistics in the model summary table, and we need to know which one of those we need to use. So for our first model, the ANOVA table, well, what is always in the ANOVA table? It is basically testing a null hypothesis about the R-square value of the model, which for the first model is just the improvement in goodness of fit from our model 1, again, to compare to the most simple model that we can think of, this model 0, where we're just using the mean of satisfaction with government as a prediction. Yeah, this is already something that we discussed in the previous lectures that you already applied, so you already know this. So this is testing a null hypothesis about R-square. So we have an F-test statistic in this case of 100,36, which you might have guessed already, if you're really super awake at the moment, is exactly the same as the F-change test statistics that we get, because in this case it's the same comparison that we're making. The most simple, having the first model that we estimated with independent variables, in this case one independent variable, compared to the most simple model where there's no independent variables at all. So for the first model, the F-change statistic is going to be exactly the same for that you get for the for this p-value, for this sig F-change in the model summary table, as the one that you get in the ANOVA table for just this p-value that you get here, because they are testing basically the same null hypothesis about the explained variance in our first model which is the same thing as the change in R squared, the null hypothesis about the R squared change, because the null model with no independent variable explains no variance, and now our first model explains some variance. So those are actually identical, again, because we're making exactly the same comparison between nested models. But for the second model, now you will see that this is actually a different F statistics than we got in the previous table, in the model summary table, because now this tests a different null hypothesis. This tests a null hypothesis about the R square value and not the R square change value. And for our second value, we already saw that R square and R square change are two different values. So R square, the proportion of variance explained by our entire second model in our sample. So this 7.1% that we just had, and this is this ANOVA table tells us something about testing that R square value against the null hypothesis that R square is 0 in the population, that we explain no variance whatsoever in the population. So again, comparing now our model 2 to the null model, to the most simple model that we think of, the model where we're not explaining any kind of variance, where we're just using the mean as a prediction for our dependent variable. So this tests now really a fundamentally different null hypothesis, a different question that is being answered with this test in the ANOVA table than with the test that we have in the model summary table. Now you also see that for this null hypothesis, we get an F value of 43.483, which is really also a completely different value as the F change value that we got for the second model, because that tests really a different null hypothesis. So it is really, really important to always be aware about, well, what is the formal hypothesis that I'm actually trying to test? What is the exact null hypothesis and the alternative hypothesis that I'm trying to test? Because that has implication for what is the correct test statistic that I need to calculate or let SPSS calculate for me. And of course, the other way around, if you want to understand what SPSS is spitting out at you, what all these different values means, it is really, really important to think about, well, what are the null hypotheses that SPSS is trying to test with these different values. Again, something that, it's going to be maybe a little bit daunting at first, all these different potential F values and different model comparisons that we could be making. But as always, assignment, practice, ask questions, and it will come to you. The nice thing is also that we'll now, if you have asked SPSS to estimate two models after each other, we get also a coefficients table where all the estimates for all the models are presented to us. So now we get a coefficients table where there is an additional horizontal line, and we have a model 1 and a model 2, which will be the first and the second model that we asked SPSS to estimate. So we have our first model, and the coefficients for that we find in the top part of the table, and we have our second model, and the coefficients we find for that are in the second, in the lower part in this case, of the table. And for both of these models we get the B0 and B1, and in case of the second model, B0, B1, B2 and B3 coefficients. So the coefficient for income in the first model, where we just had income as an independent variable, and the coefficient for income in the second model, plus the coefficient for age in the second model, plus the coefficient for happiness in the second model, because the second model we included all three of those variables at the same time. And now you see that actually the income effect did change a little bit more substantially than we previously saw. We now see that if we adjust for differences in age and happiness, that actually our income effect decreased from 0.167 to 0.138. So in other words, holding the effects of age and happiness on satisfaction with government constant, for every 1 decile increase in household income, the predicted value on satisfaction with the national government increases by 0.138 points. So now, of course, we have to take into account in our interpretation that we included more variables. So we are controlling or adjusting for differences in these variables that we are able to observe. So the interpretation of the coefficient changes accordingly. And you also can see that now we have more than one beta value. And now is also, you see that, now we can nicely compare, well, which of these variables has the largest standardized coefficient, because roughly speaking, with all the ifs and buts that I just discussed, the one with the largest standardized coefficients is the variable with the largest effect that's best able to explain differences in satisfaction with the national government. So in this case, you see, well, income has the largest standardized coefficient, happiness has the second largest one, and the smallest one we find for age. So basically, income is the best predictor of satisfaction with national government in our sample. Happiness is the second biggest predictor, and age is the smallest predictor. Is the least able to explain differences in satisfaction with the national government. So that's how to interpret that regression output. Another topic that we touched on already is this idea of multi-collinearity. Great word to pronounce. Multi-collinearity, which is a fancy term for we have overlap in the parts of the dependent variable that all our x variables are trying to explain. So there is some part of the variance, the differences in our dependent variable, where the differences in independent variables go together with between one independent variable and another independent variable go together. So we're not able to isolate the unique covariance. So that's the problem of multicollinearity, when there is too much overlap in your x variables to get reliable estimates. And what does that mean? Well, it means that we get inflated standard errors. So large values for our standard errors. Remember, our standard errors express basically the amount of uncertainty we have in our estimates. So how spread out our sampling distribution is, how far removed from the true population coefficient each hypothetical regression coefficient that you could find from all possible samples would be. So that's the sampling distribution, and standard errors basically tells you about the width, the dispersion of that sampling distribution. So the larger your standard error is, the more spread out your sampling distribution is, which means that the more spread out the sampling distribution is, the more all over the place our regression coefficients will be relative to the true population regression coefficient, so the less trustworthy each individual sample coefficient will be. So the less we can trust our regression coefficient as being a good reflection of the true population regression coefficient. So larger standard errors means that coefficients become less trustworthy. And what does multicollinearity do? Well, it increases the value of our standard value. It's going to inflate our standard errors, so indicating that we have more imprecision in our estimates because we don't have enough unique information about the effects of each of our independent variables. And now, of course, the question that I need to answer for you is, okay, we're going to, we are including multiple independent variables because to some extent we already expect there to be a correlation between those independent variables. That's the idea of multiple regression in the first place, right? That we have, for instance, potential confounding variables. Well, what is a confounding variable? It's a variable that has an effect on our dependent variable and on our independent variable. And of course, if a confounding variable theoretically has an effect on our independent variable, so if there's a z variable that has an effect on our x variable, it also means that there's going to be a correlation between our z and our x variables, between our confounder and our independent variable that we want to test hypothesis about. That was the whole reason we needed multiple regression models if we want to make better causal inferences in the first place, because there might be a correlation, an effect of a z variable on an x variable, on a confounding variable, and the variable we try to test hypothesis about. There's probably always going to be at least some correlation going on between our x variables. So the question is not so much is there any, and is there by implication any kind of multicollinearity? The question is not if, but by how much. So we need to think about ways of finding out just how much collinearity is going on. And is it something that we need to actually worry about? So unless variables are perfectly uncorrelated, x variables are perfectly uncorrelated, which is almost never the case, there's always going to be some degree of multicollinearity going on. So the question is really, when do we really need to start worrying? And there's a couple of ways of trying to check whether it's a problem. And one very unsophisticated way is, well, If the problem of multicollinearity is a result of different variables in our models being correlated, well, then just look at how highly correlated they are. So we could just calculate all our Pearson's correlation coefficients for all combinations of independent variables we put in the model, and then look at, well, are there any kind of independent variables that are very, very highly correlated with each other? Because including both of those, all of those variables at the same time might create a problem with multicollinearity. So in the example that we just saw, where I used age, income, and happiness as independent variables, I might have also, well, just checked, well, what are the correlations between age and income, and age and happiness, and income and happiness. Basically, yeah, get a correlation matrix of all those independent variables and see, well, are there any independent variables that show a really, really high correlation coefficient? Because those might create problems if I include them in the same model simultaneously. Those might lead to an issue with multicollinearity. So it's a bit unsophisticated because it's not necessarily the correlation itself that causes the problem, but only that part of the correlation where it's also going together with the same variance in the dependent variable, so the same differences in this independent variable. But roughly speaking, yeah, if variables are highly correlated, there is much more of a risk of also a multicollinearity issue. And if they are perfectly correlated, so if the correlation is 1, the Pearson's correlation, then there will by definition be perfect multicollinearity, which means you won't even be able to estimate any coefficients at all for those variables. You will just get an error message if you try that in SPSS. Yeah, so that's a rough but quite nice way of having a first check. If you're working with multiple X variables and you want to do multiple regression analysis, just first start out with a correlation matrix for all your independent variables to check whether there are any potential issues with independent variables that correlate quite highly, because then you are already aware that you need to be a bit careful with whether or not you can include those variables in the same model at the same time. There are some more sophisticated ways of trying to figure out whether it's an issue. Like I said, the correlation coefficient is related to the degree of multicollinearity, but it is not necessarily always the same. So there are also ways of trying to get some kind of value that really is a direct reflection of how much multicollinearity you have. And there are two of them that are quite commonly used, the so-called variance inflation factor and the tolerance measurement. So these are two different values that you can calculate that tell you something about the degree of multicollinearity you have with your independent variables that you included in the model. Now, why is the variance inflation factor called the variance inflation factor? Well, where does let's start with the inflation. Where does the inflation word come from? Well, remember, what is the problem of multicollinearity? The problem of multicollinearity is that it leads to inflated standard errors. So what does this VIF score, often referred to as the VIF score, the variance inflation factor, what does it try to do? It basically tries to show, well, okay, by how much are the standard errors inflated? And how are standard errors estimated? Well, the estimate of the standard error depends, as you may remember, on the sum of squared residuals of the model. We went over that formula for a simple linear regression model, but also for multiple regression models, the same logic applies. We are looking at the variance of the unexplained variance basically around our regression predictions. Those go into calculating the standard errors. Yeah, if there's more differences in our dependent variable that are left unexplained, then that will increase the variance around our regression prediction. So that means that our standard errors will be larger, indicating that there is more uncertainty related to the value of the coefficient that we are estimating. So estimating a standard error is based on a variance, the variance that basically the unexplained variance around the regression prediction. So the word variance inflation factor basically tries to quantify by how much is that variance that we use to calculate the standard error inflated. So basically by that having a rough idea of, well, how much is the standard error inflated. So that's a more of a precise measurement of multicollinearity. We also have the tolerance value, which I will come back to. Which I will come back to. I first want to talk about another way of checking this multicollinearity where it's an issue, and it's really, really unsophisticated. But it's one that tends to, in practice, once you have a bit of experience and you know what to look for, tends to work sometimes even better than just using these correlation matrices or looking at the VIF scores or the tolerance values, because they tell part of the story, but they don't tell the whole story. So you might have a situation where even though the Pearson's correlations are quite low between your independent variables, and the VIF even the VIF values don't look terrible, are not super high, you still might have an issue with multicollinearity. And the other way around, you might be in situations where you have very high VIF values and high correlations between your independent variables, but there still really isn't an issue with multicollinearity, because there are other factors that go into that and what is being captured by the correlation coefficient and the variance inflation factor. One of those factors being the sample size itself. The larger your sample is, the less of a worry that you have about multicollinearity, because multicollinearity is a problem of insufficient information, insufficient unique information. But adding more observations increases the amount of information that we have. And remember, variation equals information, and more observations equal more variation. So that's one of the things that also go into the question of whether or not multicollinearity is an issue. So there is a way, once you have done a lot of regression analysis, that works often quite well in spotting whether or not you have issues with multicollinearity. And that's just adding your independent variables step by step. So if you want to, for instance, you think, I'm going to have a model with 20 independent variables, then just add them one by one. And then carefully watch what your estimates and doing. So your estimates for the coefficients and for the standard errors. Because what you will often see if you have a problem with multicollinearity is that at that moment where you add the variable that is problematic, so where there's too much overlap with one of the variables that is already in the model, once you add that model, then all of a sudden you will see that the standard errors explode, so get really, really large values sometimes, or that you will see that you get coefficients estimates which are super, super weird. So for instance, you had a nice positive effect of satisfaction of income and satisfaction with government, which is also something that you theoretically would probably expect. And then you add one variable, and all of a sudden the standard error becomes super large for the income effect, and all of a sudden you get a really, really large, super unlikely negative coefficient. That's a sign that there is an issue with multicollinearity. Again, this is one that you need to do it a lot and to have seen it a lot happening in practice before you can really use that method well. But once you do, it can sometimes be even better than just looking at Pearson's correlations and variance inflation factors. Yeah, so that's something that I'm telling you now already, but it's something that will probably only be useful to you once you start doing lots and lots of regression analysis and encounter the problem of multicollinearity in practice a couple of times, because then you will start to recognize the signs of that. Yeah. So the variance inflation factor tells you by how much the variance that is used to calculate the standard error for each of your coefficient is inflated. Yeah, remember, the standard error is based on a variance, the variance around our regression prediction, that's what we're using to calculate the standard error. And multicollinearity basically blows up that variance and thereby blows up the value of the standard error. So the variance inflation factor tries to tell you, well, by how much is the value of the standard error blown up? By how much has it increased due to multicollinearity? So the larger the VIF value is, the more you have an issue with multicollinearity for the estimated effect of that specific independent variable for which you are estimating for which you're calculating this variance inflation factor, because you will get one for each of your X variables. And of course, then the question is going to be, well, when is it an issue? What value do I need to look out for? And as always, my honest answer is going to be, well, it depends. It depends on lots of different factors. Like I just said, for instance, also the sample size goes into whether or not multicollinearity is a problem. The true effect size also go into whether it's a problem. So if you have, if the true population effects are very, very large, then there is a little bit less of an issue with multicollinearity than if they're very, very small. Of course, you don't know the true effect sizes. So there's always a question about, exactly when is it too big? And there is no hard answer for that, but there are some, let's say, useful rules of thumb that you might want to think about. So again, it depends, as it always does. So if you want a rule of thumb, I can give you one. I would really start to worry if my variance inflation factor goes over 10. But that's really a rule of thumb. So if I have a super large data set, then and I don't see anything weird happening with my estimates, then I might not worry even though my VIF value goes over 10. If I have a really small data set, then I might be worrying even if the variance inflation factor is a value of 5 or 4. Yeah, so it really depends also on those things. But as a rule of thumb, if it goes over 10, then you might have an issue. But if you read different statistics books, you will see that every one of them gives you one rule of thumb and all of them are different, which also indicates that, it really depends. There are no hard rules about that. You have to use it as a tool for you as a researcher to make a decision about whether or not you have an issue with multicollinearity. And of course, if in doubt, the safest way is always, then just estimate models with the variables included and without the models included and present both. So you can actually show your reader what's going on, but of course that still means that you have to draw some kind of conclusion. So you have to think about, well, what model is better and what model is maybe suffering too much from multicollinearity. So that's again a choice that you have to make based on your knowledge about the data and the potential issue of multicollinearity. As always, statistics are just a tool for you to make a decision, but at the end of the day, you have to make a decision. And of course, it helps if you know how the tools work. But at the end of the day, well, there's a decision you need to make. And then, we talked about also the tolerance value. So that's another way of trying to express the degree to which multicollinearity is an issue. And really, the reason that we have a tolerance value and a VIF value is just stupidity, because different people worked on a solution of trying to quantify multicollinearity, and then some people tried to express that on a scale that indicates an inflation in the variance used to calculate the standard error, and other people tried to, so then it's a larger value means that there is more of a problem, and other people tried to express it on a scale that indicates to what degree your let's say your standard errors are robust or tolerant to having overlap in your independent variables. So there is a direct mathematical relationship between the VIF factor and the tolerance factor. Tolerance is just 1 divided by your VIF factor. So if your tolerance goes up, if your VIF factor goes up, your tolerance goes down. So the more the variance is inflated, so the more multicollinearity you have, the less tolerant your standard errors are to that inflation, so the more of an issue with multicollinearity you have. So tolerance is directly mathematically linearly related, directly proportionally related to the variance inflation factor. So both of these numbers capture exactly the same thing, just expressed on a different scale. And it really doesn't matter which one of them you are using, as long as you know which one you're using and how to interpret them. But they both give you exactly the same information. So there's really no other reason than, well, a historical coincidence, and that we have both of these values, that we have tolerance and VIF. And I think it also has something to do with keeping statistics teachers employed, so they can explain all these needlessly large number of different statistics that tell you exactly the same thing. So I'm happy about that, but you probably are cursing the field of statistics, and you rightfully should be doing so. So that's that. Again, the see you Monday, no, because we don't have any physical lectures, but I will be seeing you next Friday, and good luck with everything. Bye-bye.